We will now do the second part of our probability review. This one deals with random variables. We got two kinds of random variables, discrete and continuous. On our formula sheet, of course, those first two formulas deal with basic probability, which we did in our first video. These are the two formulas that we're going to be using in this video, and both these deal with discrete random variables. This is the mean, otherwise known as the expected value of a discrete random variable, which is going to be our first example, or our first context actually that we're going to look at. And this is the variance, in other words, the square of the standard deviation, and so we are going to use this formula to find that. And then we have the three binomial formulas, which is going to be, we're going to do that in a future video. That is also a part of probability. And then, by the way, we've got our sampling distribution formulas, which is going to be as we go into statistical inference. But so let's look at a context, and let's look at the next major area of probability, which is random variables. So the number of customers that a store has in an hour follows the discrete random variable below. Discrete means it has a countable number of outcomes. A random variable is just something that's producing a number. And if this number is countable, like in this case, it's either going to be 0, 1, 2, 3, or 4, then it's discrete. It has a countable number of outcomes. If it was something like people's weights, where it could be like 152.576 or 187.21, it can take any number in an interval, then it would be continuous. But we'll look at examples of that in a minute. But so this is a discrete random variable. So the first thing they could do, so what this is saying is here's the number of customers they could have, either 0, 1, 2, 3, or 4 in an hour. 30% of the time they have 0 customers. 30% of the time they have 1 customer. 20% of the time they have 2 customers. 10% of the time they have 3 customers. 10% of the time they have 4 customers. A lot of times they'll give you a very basic sort of question. It'll be like, all right, if you randomly select an hour, what's the probability they have, let's say, more than 2 customers? Well, more than 2 customers, that'd be 3 or 4, and so you would just say, well, that's 10% plus 10%, 20%. That's what you would say, or you could say 0.2 or 2/10. And so then it'll follow that up with some question that's a little more complicated, like number 12. If you randomly select an hour, what's the probability there are more than 2 customers given there's at least 1? And so the notation that we have talked about before, the probability more than 2, that x is greater than 2, given that, so that's that vertical line segment, that x is greater than or equal to 1. All right, and so our little formula for our conditional, which we talked about last time, which is on your formula sheet, is the probability of both of those things, that and that, the probability that x is greater than 2 and that x is greater than or equal to 1 over the probability of your given x is greater than or equal to 1. Well, think about this. What's the easier way of saying that something's greater than 2 and it's also greater than or equal to 1? If you know something's greater than 2, it obviously has to be greater than or equal to 1. So the easier way of saying this is just the probability that x is greater than 2. If it's greater than 2, it has to be greater than 1. And then the bottom would stay the same, x is greater than or equal to 1. Well, what's the probability that x is greater than 2? And so that is going to be, well, it's 3 or 4, and so it's 0.2. What's the probability that it's greater than or equal to 1? Well, that would be this, or this. So you add those up, and it's 0.7. And so that, in fact, if you were to make that a decimal, that, in fact, would be equal to 0.28571, 0.28571. So these conditional problems like this with random variables, it's in essence just going to be the probability of that over that. All right, so, and then what are the mean and standard deviation of the number of customers? And that was those formulas we talked about on the formula sheet. The formula for mean is just the sum of your x times your p's. That sigma means sum x times p. So what we'll do is we'll just find x times p's, and we'll add them up. And so it's just that times that, and so that would be 0. That times that would be 0.3. That times that is 0.4. That times that is 0.3. And then that times that is 0.4. And then if we add them all up, we got ourselves the mean. Add them all up, and so that'd be 0.7. That was 1.4. So our mean is 1.4. And you would leave it like that. Don't round it. It's a mean. It's an average of a large number of followings. So like that's especially tempting to do if it was something like 4.1. And say, oh, we're expecting 4 customers. No, don't round it. The mean is an average of a large number of trials, not so much what you're expecting for just 1 trial. So anyway, now the standard deviation. And that's that other formula. So the formula first of all, for our variance, the square of the standard deviation, that's the way it's given on your formula sheet. It's the sum of every x minus the mu, what we just found, squared times p. So it's sort of tedious to do. So let me show you if you're doing it by hand. Now I'm going to show you a shortcut with your calculator, but you have to understand what I'm fixing to say in regards to using this formula. So take every x value and subtract the mean. So we'll take 0 and subtract 1.4, the mean, square it, and multiply it times that. Now when you do that, let's see what that is. And so when you do that, you would say, 1.4 squared, and then go times 0.3, and so that's 0.588. So that's 0.588. And then you do the same here, 1 minus 1.4 squared, and then multiply it by that. And so that is just going to be, negative 0.4 squared, so it'll be 0.4 squared, and then times 0.3, and so that would be 0.048. And you would continue to do that for all of these. I mean, it's a bit tedious, it's not hard, and add them up, and that would give you the variance. And you take the square of that, you keep going, take the square of that, take the square root of it, and gives you the standard deviation. Now, let me show you the little shortcut with your calculator. What you can do is you can go to a list, so I'll hit Stat, and then hit Edit, just like we're entering things into a list, and put your x values in list 1, and then your probabilities, your proportions, in list 2, just like that. And then we will do one variable stats and find the mean and standard deviation of these. And so just like we ordinarily do one variable stats. So we go Stats, Calculate, and one variable stats of now. We're doing list 1 and list. This is the only time all year we put list 2 there. Remember, you got to clear it out otherwise. So it's a common area to have that there when you shouldn't. All right, and so second list 2. So what this is telling the calculator, it's the x values in list 1, and this is how often the x values are occurring. Okay, and we get calculate, and so there it is. There's our mean, and there is our standard deviation. That's the only time we'll use that sigma. That's our standard deviation, 1.2806. So the standard deviation is equal to 1.2806. So there we go. And so that is in essence the average amount that our values are varying from 1.4 if we looked at a large number of values. All right, so now let's talk about transforming. All right, when you double a random variable and add 5. So if you doubled the number of customers and add 5, what would the new mean and standard deviation be? In other words, if you took these numbers, multiplied them by 2, and added 5, and you'd have the same probabilities. Now you could do that very thing. You could just go to list 1, multiply everything by 2, and add 5, and find the mean and standard deviation. But you have to understand what I'm fixing to say here. When you transform random variables, what happens to the measures of center and the measures of spread? The mean of 2x plus 5, the measures of center are affected both by multiplying and adding. So like the mean and median, let's say. So the mean of 2x is just 2 times the mean, which is 1.4, and then plus 5, and that is equal to 7.8. And then the standard deviation, though, the standard deviation of 2x plus 5, the plus 5 does not affect measures of spread. Measures of spread are not affecting by adding, subtracting. So it's just going to be 2 times 1.2806, and so that is equal to 2.561. So that is our new standard deviations. Measures of spread, such as the standard deviation, the IQR, and the range, are not affected by addition or subtracting. They're just affected by multiplying. And so there we go. That's an important fact there. All right, now let's talk about continuous random variables. They could take any number in an interval, in essence decimal numbers. All right, so Hideo has a large number of poodles and beagles. His poodles have weights that vary approximately normally, okay, with a mean of 34, standard deviation of 3. The beagles have weights that vary approximately normally, so that would be a continuous random variable as well. Mean of 38, standard deviation of 6. Assume these weights are independent. Okay, we'll talk about that's really important. Now we can combine them if they're independent. If you randomly select a poodle or beagle, find the probability of that. And so here is our problems that deal with the poodles and the beagles. Okay, now find the probability that the sum of their weights will be less than 65. So the sum of their weights. So what we're going to do, let me write down what our variables are. And so in regards to the poodles, they vary approximately normally, and they have, see, a mean of 34, standard deviation of 3. So mean of 34, standard deviation of 3. And then the beagles, okay, the beagles, they vary approximately normally, and they've got a mean of 38, standard deviation of 6. 38, standard deviation of 6. And so we're interested in the sum. So what we're going to think about is a random variable poodles plus beagles, the sum. Well, when you add together two normal curves, the result is a normal curve, and you can just add the means, and that's 72. But you can't add the standard deviations. You have to add the variances. This, in my opinion, is why the variance even exists, is because you can add the variances when you combine curves. So our variance, the square of the standard deviation is 3 squared or 9. That's our variance for our poodles. Our variance for our beagles is 6 squared or 36. And then the variance for poodles plus beagles, you add those. And you can do this only if the variables are independent, and it clearly said they're independent. If they weren't independent, then you'd have to, it's a more complicated formula, which is not in the AP Stats curriculum. But we would, so we add the variances, so the variance of this is 45. Therefore, the square root of that is the standard deviation. So that is our new curve, the sum. And so what's the probability the sum would be less than 65? What's the probability that poodles plus beagles will be less than 65? Well, we'll do normal CDF. Now, you could be asked to show your work here by drawing the curve and showing the z-score, but if not showing your work, you can just write normal CDF and label your parameters. Less than 65, that'd be negative infinity to 65. Our mean is 72, and our standard deviation is the square root of 45. Label this lower bound, upper bound, mu, and sigma. It's important that you label it or you only get partially correct. And so what the heck, let's do that with our little calculator. So we will do second distribution, get to normal CDF, you go to distribution there above the vars button, second distribution, normal CDF, and so we're going negative infinity. And so hit the negative button, not the minus button, that'll give you an area. They're negative, and I'll just go like negative 9 trillion. That'll certainly be effectively negative infinity. And then the upper value is 65. So I go 65, and then the mean is 72. And then the standard deviation is the square root of 45. And so then we hit, there we go, like that. And so we get 0.14836, approximately 0.14836. Boom. And that's how you do it. Okay, then it says this, what's the probability the poodle weighs more than the beagle? So we're expecting, in general, on average, the beagles weigh more. So we're expecting, if you randomly select a poodle and a beagle to weigh more most of the time. Not all the time. It could be, let's say the poodle is one standard deviation above the mean. It'd be 37. That's not that unusual. And then the beagle is one standard deviation below the mean. It'd be 32. In that case, the poodle would weigh more. It's not going to happen more than 50% of the time, but it'll happen. Whenever you're, the probability that one curve is more than another, you're going to subtract the two curves. And so I'm going to say we have a new curve, poodle minus beagle. You could go beagle minus poodle, and that would work out fine as well. When you subtract two normal curves, and we can do them because they're independent, all right, the result will also be, the result will be a normal curve. You subtract their means. This is negative 4. And this is a bit counterintuitive in regards to the standard deviation. You still add the variances. We're in essence combining the variabilities of these curves. So you still, even when you subtract two curves, you add the variances. So the standard deviation is still the square root of 45. And so if poodle weighs more than beagle, that means P minus B is positive. And so in essence, what's the probability this thing is positive? P minus B is greater than 0. And so that would be normal CDF. And so that would be as greater than 0, so that would be 0 to infinity. Our mean is negative 4. Our standard deviation is the square root of 45. LB, that's lower bound. That's upper bound. That's mu. That's sigma. And when you do that, you would get, it's 0.2755. 0.2755. So it's certainly a plausible thing that can happen, but it doesn't happen most of the time. So that is subtracting two curves. So then the next thing, the last thing in regards to this is when you select three objects from a normal curve, what happens there? If you randomly select three beagles, what is the probability that the sum of their weights will be greater than 120? Okay, so in regards to three beagles, okay, three different things. All right, the sum of those three beagles will also very normally. All right, the mean is going to be 38 times 3. All right, so the mean is going to be 114. But when you're taking three different objects, you don't multiply the standard deviation, you multiply the variance. Each of these three beagles is adding its variability. So, in other words, the variance, so you would say that, okay, the variance of the beagles is 36. And so for three beagles, so three of that, so for three beagles, the variance is going to be 36 times 3, 6 times 3, and that is equal to 108. So that is our variance, and so that's the square root of 108. This is a distinctly different problem than taking one beagle and multiplying it by 3, which that's what we did when we did the 2x plus 5 thing. We were multiplying a distribution by something. So if you're taking one beagle and multiplying it by 3, then you multiply the standard deviation by 3. But we weren't taking one beagle, we were taking three different beagles. Okay, and so that's a different situation, and so there's our mean of standard deviation. So what's the probability is greater than 120? So it would be normal CDF, and so that would be 120 to infinity, mean of 114, standard deviation, root 108. Properly show your work. This would be lower bound. This is upper bound. That is mu. That is sigma. And let's see what you get when we get that. So this would be normal CDF. And so that would be 120 to infinity. I'll just put like 9 trillion. The mean of 114. The standard deviation would be the square root of 108. It's like that. And so we get 0.28185. 0.28185. Right like that. So that's how you do that problem. And then lastly for this video, let's talk about a uniform curve. So in regards to random variable problems, in essence we've got discrete ones, we've got and then we got the two continuous ones that are the main thing we do is normal and uniform. Now there is an indefinite number of different kinds of distributions and curves, obviously, but these are the two that we have to work with the most. And so when you're working with these, it's in essence sort of working with areas. But so this says the time that people in the city watch TV each night follows a uniform. Uniform is not normal. It's just straight across. Distribution that varies from 0 to 4 hours. If you randomly select someone from the city, what's the probability they spend more than 2.5 hours watching TV given they spend more than 1 hour? So our distribution is looking like this. It is just the numbers 1 through 4. 0, 1, 2, 3, or 4. But it's continuous. It's not just exactly 0, 1, 2, 3, 4. It could be 0.5 or 0.52 or 2.617 or whatever. It's every number between 0 and 4. And it's uniform means it's a rectangle. It's just going straight across, right like that. And so whenever I encounter uniform, I just make a rectangle and think about the areas in the rectangle. So this says this. What's the probability they spend more than 2? What's the probability they spend more than 2.5? Given they spend more than 1, given that x is more than 1. And this is what this is going to be. Similar, it's that and that, the probability that x is greater than 2.5. And so it isn't, and so what's the easier way of saying something's greater than 2.5 and it's also greater than 1? Well, it's just greater than 2.5. So what it in essence is going to be in this case, it is the area greater than 2.5 over the area that it is greater than 1. Well, what's the area greater than 2.5? Well, if you think about this rectangle, and we'll just say the height of this rectangle is 1, just for convenience. So here's 2.5. It's right there. Okay, what is this area of this thing right there? Area greater than 2.5. Well, that would be, the base here is 1.5 times 1, so it is just going to be equal to 1.5. And then what is the area greater than 1? Well, the area greater than 1, that would be here. And so that would be 1, 2, 3. So its length is of length 3 and its height is 1. So it's 3. And so this would be that divided by that is 0.5. So if you were to randomly select, okay, let's say here's our rectangle. If you randomly select a point that is in the shaded rectangle here, lightly shaded rectangle, what's the probability of being in the dark shaded area? And so the area, it's be 1/2. So that is that. Now, by the way, with continuous random variables, there's no difference in greater than or equal to. That'd be the same thing, because the area of this line segment is 1. I'm sorry, the area of this line segment is 0. It adds nothing. It's a bit of a paradox. It adds nothing to the area of this triangle. Same thing if this is greater than or equal to. It'd still be the same thing, okay, because the area of the line segment is 0. It's not adding anything to the area there. So greater than or equal to, same thing as greater than, okay? Now, it's not true with discrete. With this, it was distinctly different, okay? But, so there we go. Okay, that's it for the probability review video 2. So thanks for watching. Hope you enjoyed it. And we got one more probability review video.